the value of a coalition only depends on the size of that coalition, right? And not on the identities of the players who are the members of that coalition. And then we said that if in such game we have a non-empty core, then the equal division of the value of the ground coalition would be an element in the core. And we also said that for those games, the same payoff vector would also define the Shapley value, which now means that if the game has a non-empty core, then the Shapley value is also an element in the core, which is not always true. So if such a game has a non-empty core, then the Shapley value is not only the fair division of the payoffs, it's also a stable division of the payoffs. And that's a nice thing. And then we talked a little bit about cooperative games that are defined on some underlying non-cooperative games by giving each coalition the value that is equal to its safety level, to its maximum value in the coalition. You remember then when we talked about maximum strategies and maximum values, we can restrict ourselves to few strategies, as always. If, you know, in the context of the game, it does not make sense that mixed strategies are allowed, then we can restrict ourselves to few strategies. And then we can define the safety level only among the few strategies. In general, though, maximum strategy can be a mixed. So when we spoke about cooperative games defined on a class of congestion games, we spoke about safety level strategies which are pure. And then the last thing that we said was that if the value of the coalition, if coalitional values in such a game are easy to compute, then it will be easy to decide whether the core of the game is empty or not. And then using the other facts, if we know that the core is non-empty, then of course it is easy to find an element in the core, the equal division of the payoffs, and then it would also say that the Shapley value is in the core, and it is also easy then to check whether any given payoff vector is a member of the core. Let me show you why this is true. If that's easy to find the value of the coalition, then it would be easy to decide about all those things. Okay. So we have an anonymous game, right? And that's why the characteristic function, that's actually a function of the sizes of coalitions, right? So this is just, in fact, a list of n+1 numbers. So now let us take some imputation, some feasible payoff vector P. So we know that the sum of those values is exactly the value of the ground coalition. And also for each subset, for each coalition C, the sum of payoffs must be at least as the value of that coalition if we want this imputation to be an element in the core. Right? So we need to check that. Similarly, this condition requires an exponential number of tests for each collision. Right, so for each collision, I have to compute those numbers and check if that's in the core. But in our case, what I can do, I can just, in fact, order the elements in the player set, I1, I2, and so on, In, by their imputations, by their payoffs given this imputation. Okay. And now, instead of checking this condition for each collision C, I can check this for every collision of size K, where I will take only the beginning of this sequence. Because if the condition holds for such a collision of size K, it will hold for any collision of size K. And we only have values for sizes of the collision, and so the computation becomes easy. Right? So this is to check whether a given imputation is in the core. So the same way, we then can check if the element where we just divide the value of the ground collision equally among the members of the player set, if it is in the core, it will be a polynomial time computation, right? If it is in the core, then by the previous theorem we said, then the core is not empty. Well, that defines that the core is empty. If it is not in the core, that's an important, then we would know that the core is empty. Because if it was not, then this element should have been in the core. Right? So if it's in the core, then we are fine. If it is not in the core, then we know that the core is actually empty. Okay. And then the Shapley value, of course, is not an element in the core. So that's about anonymous cooperative games. Now, when we talk about games which are defined on congestion games, then we said the following thing. If the underlying congestion game is symmetric, then the corresponding cooperative game is anonymous. And then all the beautiful things that we said before that would hold, right? What is a symmetric game? So for non-cooperative games, we also have the notion of anonymity, which is different from that of cooperative games, but the essence is the same. The identities of the players do not matter. That means that the strategy of a given agent would only depend on the partition of his opponents between different strategies. Right? A game would be symmetric if, for any permutation of agents, we would have the same utilities from the strategy profile. Say, the utility of agent I from the profile S1, Sn would be the same as if I just changed the names of the agents and shuffle them differently among the strategies. Okay. So why anonymous and symmetric games are not the same notion. For instance, in congestion games, anonymous means indeed the strategy that I would take, trying to maximize my own utility, would depend on how many agents I have on each resource, and it does not depend on their identity. Right? Having symmetric payoffs would require that also all the agents have the same strategy space. So they are able to choose from the same set of resources. Because otherwise it can be the case in congestion games, we know that the strategy spaces of two different ages do not have to be the same. Okay? They're all subsets of some given superset of resources. If they are the same, then we may have symmetric utilities. If they're not the same, it could be the case that one agent can use resources A and B, another C and D, and if we are not just able to shuffle them and give them to play other resources. Okay, so symmetric congestion games would be congestion games where all the agents are allowed to use the same set of resources. And now, if we have symmetric congestion games, then the cooperative games that they define would be anonymous, and we have all those things. Now, we said that it would be easy to decide about the non-emptiness of the core and so on if it's easy to compute the value of the values of collisions in such a game. Now, the thing is that it's not always the case. So if we look at symmetric resource selection games, then computing collisional values is easy indeed. If we take symmetric congestion games, which are not necessarily resource selection games, so the agents may use more than one resource, then it becomes already very hard. And if you bear with me, I'll show you why. We never had any hardness proof so far. And if I reduce the assumption of symmetry, then even for resource selection games, this becomes hard. But let me show you this. So I remember when I asked you if we know what NP hardness means, you all said yes. Right. And then I would assume that you also know what's the general technique to show that some problem is NP hard. Okay. So for some problems it have been, so for some of them it have been decided using direct definition with Turing machines that they are computationally hard, NP hard in particular. And so we do have some set of problems for which it is known that they're hard. Okay. Given that, for a new problem that we have, we do not actually need to use the direct definition and to deal with the definition of the Turing machine to show that it's hard to solve that problem. We can use a reduction from some known hard problem to our problem. Now, when I mean what I mean by reduction, I need a polynomial time mapping of a known NP hard problem to ours. Why would that be enough? Because if our problem was and there is a polynomial time translation of some other problem to ours, then we could translate that problem to ours in polynomial time, solve our problem in polynomial time, and that would give us a solution to this problem. Okay? So if such a polynomial time reduction does exist, and we know that that problem is hard, then that would follow that our problem is also hard. Is that clear? So that's the way to show hardness of problems. And there is one problem that you might have heard about, and it's very useful in these sort of reductions. It's called exact recover set, and the notation is x3c. That's for exact, that's for 3, and this is for cover. And the problem is as follows. So we have a ground set, how do I call it? Let's call it x, that has 3m elements. So it's a multiple of 3. 1, 2, well, let's call them x's. x1, x2, and so on. x3m, where m is a natural number. So we have a ground set of those elements, and we also have some collection, let me call it R, of subsets of X. Each of them has exactly 3 elements, okay? But they are not necessarily disjoint. There are n of them, where n does not depend on m in any way. It's just large enough so that the problem is not trivial. So we have R1, R2, so on, Rn. N is an actual number. Now every Ri is a subset of the ground set X, and the size of Ri is exactly 3. Now the problem is, so that's a decision problem. The problem is to decide whether there exists a collection of R, of elements of R, I1, I2, and so on, exactly M sets. Okay, now this is the same M as here. So if I take the union of that collection, then I will have exactly 3M elements. Right? But some of them may appear more than once. And so the decision is whether there exists such a collection that will cover the ground set, meaning that all those guys are disjoint. Okay. So that it exactly covers the ground set. And we want exactly M sets in there. So now what I want to show that given such a problem, I can construct an instance of our problem so that whenever I have the answer yes here, I can say something about our problem, and every time that I say no here, I would need to say something else about our problem. Okay, so that's a solution. And we constructed the following way. So I have to define now what a congestion game. A asymmetric congestion game where all the agents have the same set of resources. And I actually intentionally called this set of triplets R because this will be our set of resources. And also the strategy set for each agent would be exactly that. Right? So each agent, his single strategy would be what? A triplet, 3 resources, right? Given with this collection. Now the set of agents and we will have exactly M agents. Now I need to define the resource utility functions, and the utility of using a single resource R when the congestion is 1 will be 1, and it will be 0 for any congestion greater than 1. Now what I want to show is the following thing. So let B of M will be the value of ground collision. Defined as the safety level. Safety level in this case, there are no openings, so it's just the maximum value that the ground collision can have. And what we say that if the exact cover does exist, then the value of the ground collision is exactly 3m. If it does not exist, then the value of the ground collision will be less than 3m. And now this is pretty easy to see. If we have an exact cover, then for agent I, we can choose the strategy for it. Let me call it agent J. Here we'll choose the strategy Rij, where J goes from 1 to M. Okay. And then, given that there is an exact cover, so these sets are disjoint, there will be congestion 1 on each resource. Right? So each agent will have utility of 3. The sum of them will be 3m. This will be the value of the ground collision. If we do not have such an exact cover, then at least one of resources will appear in any collection that covers the set more than once, and so there will be congestion more than 1 on at least one of the resources, and from that resource, the corresponding agent will have the utility of 0, so the ground collision will get less than 3m. And better. So this is how we show these sort of things, and I've chosen this one because it's relatively easy. Usually people have to work much harder to construct such a reduction, but that's the principle. So you can see that many times in hardness results. But the issue about whether it's easy or hard to compute the value of a coalition given an underlying game was actually meaningful only in the case where we computed at the safety level and pure strategies. Because if we reduce ourselves to, if we allow the agents to play mixed strategies, then what essentially is the value of a given coalition? Right? We have the coalition of agents playing against the complement set, so in fact this is a two-player game. Right? If mixed strategies are allowed, then the maximum is the same as the Nash equilibrium strategy for the given agent, who is a coalition in our case, and that is as to find the Nash equilibrium in the corresponding zero-sum game for two players, and that can be solved as a linear problem, so that's not computationally challenging. Right, let's have some example, which is not a congestion game. We have 3 agents, I suppose, and each one of them has 2 strategies to play, 1 or 2. Okay, and if the combination of strategies is 1, 1, 1, then the corresponding utilities will be -2, 1, 2, and there are 8 possible combinations: 1, 1, 2, 1, 2, 1, 1, 2, 2, and 2, 1, 1, 2, 1, 2, 2, 2, 1, 2, 2, 2. And the corresponding utilities are -2 and 2, 1, 1, -1, 0, -1, 2, -1, 2, 0, 1, -1, 0, 0, 1, 1, 0, 0, and 1, 2, 0. Let us compute the value of coalition, for instance, of P1 and P3. Okay, now that coalition plays against a singleton coalition that consists of only agent P2. So I can now write a matrix of that game. So the strategy of this pair will be 1, 1, 1, 2, 2, 1, 2, 2. Where the strategies of their opponent will be 1 or 2. And we can write down the corresponding pairs, right? So if we have 1, 1 played against 1, then these guys together get 0. This guy gets 1. So we have 0, 1 here. 1, 2, 1 gives us 2 minus 1. 2, 1, 1 gives us 2 minus 1 again. Was it correct? 1, 2, 1, yeah. 2, 2, 1 is 1, 0. And in the second player plays 2. These are those cases. It's okay, I've done something wrong there. In this one. Right. So it's 1, 1, 2, 1, that strategy. So it's 0, 1. And there we get 2 minus 1. Minus 1, 2, 1, 0, minus 1, 2. And we can find, I will say was the computation I'll just say that, yeah, now we have 4 strategies for the first agent, but you can see that that this strategy is dominated by that strategy. And you can also see that this strategy is dominated by this strategy. And so we can reduce the game to just 2 strategies for both of agents, and then it's, you know how to find the mixed strategy Nash equilibria. You will have to replace the payoffs of the other agents with zeros and solve for the Nash equilibrium. And what we will get is that the value of coalition of P1 and P3 will be 4/3, while the value of coalition of the agent 2 will be -1/3. Same way, another game with the corresponding payoffs, we would find that the value of P1 and P2 together is 1 against the value of P3, 0. The last pair, P2, P3, will get 3/4, and agent 1 alone will get 1/4. Now the grand coalition is getting 1, and the empty coalition 0. Now, given this characteristic function, what coalition structure would you expect to form? So what would you expect to be as a solution of this cooperative? We may notice that agent 1, in fact, is the only agent who alone gets a positive value. Agent 2 has a negative payoff when he plays alone. Agent 3 gets 0. And each of them, when they're paired with agent 1, they actually have something positive as a coalition. So there is a hope for them to get something from that coalition, or if both of them are together with him. So actually they would try to bid and attract agent 1 to become a member of the coalition with them, separately or together. Also, agent 1, since his payoff in a singleton coalition is 1/4, would require a payoff from a coalition which is at least 1/4, right, from individual Roshanite. However, if he requires too much, then agents 2 and 3 may form a coalition together without him and get 3/4. So that's something that we would expect from the solution. And then we remember that for some games where the characteristic function is super additive, right? Remember what's that? If we have 2 sets S and T, which are disjoint, both are subsets. And then the value of their union is at least as the sum of their individual values, and so it makes sense for them to merge together. In such a case, we said that it's likely that the grand coalition would form. but that's not true for all the games. And also, even if we look at superadditive games, then this condition in particular, that's easy to check, would require then that the value of branch coalition must be greater or equal than the sum of values of singleton coalitions for all the agents. Now there is a special case of that game. So that just follows from superadditivity. A special case is when we have an equality here. And in that case, the game would be called inessential. Why inessential? Because in fact, this would imply that the value of each coalition would be just the sum of the values of singletons of the corresponding agents. And that means that although it does not harm to form a coalition, there is actually no point to form a coalition. Because they are equally well on their own. They don't gain anything from forming a coalition. Now, the game is called inessential because of this fact. Yes, it does not harm to form a coalition, there is no point to do that, but it doesn't mean that those games are not important, because in particular, such games would arise as cooperative games, which are based on underlying, non-cooperative, two-player, zero-sum games. Okay. That would give us a game which is inessential. However, if we have a game where we have more than two players, even if the sum of values of each coalition and its complement would be a constant sum, okay, let's call it, say, a constant sum cooperative game. Is a game where for each coalition C we have that the value of C plus the value of its complement is some constant C. Too many C's. Okay. Such a game may be still essential, and this is an example, for instance. The sum is 1, the sum is 1, the sum is 1, the sum is 1. So that's a constant sum game. And now you can check that this game is essential because the value of the branch coalition is 1. If you sum up the values of the singleton coalitions, you would have minus 1/3 plus 0 plus 1/4. Okay, it's not 1. So it is an essential game. And if we check the core of this game, so to solve for the core, what sum of payoffs for all the agents will be exactly the value of the ground collision, which is 1, and then we have to check that the total payoff of the collision is greater than the value of that collision. So I write that for all the collisions. And then we solve that linear system. For this particular game, we find that the core is empty. The fact is that this is not a coincidence, because if we have a game which is a constant sum and essential, the core will be empty. So instead of writing the system of equations, I would have just checked that that's a constant sum game, and it is an essential game. I'll stop here. Next week, what we do, we will talk about one more solution concept that we didn't cover last semester. So we spoke about the core, we spoke about absolute core and the least core. And there is one important solution concept which is called nucleolus. So we define that and see how to compute it in simple cases. And then we speak about different classes of cooperative games with the applications that they have in multi-agent systems, and different computational equations of computing different solutions which are relevant to those cases. There will be next week. After next week, Enrico will be with you for 3 weeks, teaching mechanism design, different mechanisms, including options, and also learning in games, so repeated games and learning algorithms, standard algorithms that the agents may apply. And after that, I will come back and speak about mechanisms without payments, mechanisms without money. One of them, one setting for such mechanisms, you already know, that's voting. Okay, so that's making some collective decision given preferences of agents without actually making any payments. And another central application of such mechanisms is what is called stable matching or stable marriage problems, or roommates problems, as how to form coalitions, allocate agents to each other, either in pairs or larger groups, given their preferences about whom they want to be together, so that the whole allocation is stable. It has the funny name of stable marriage, and we can speak about stable marriages in this model, but the real underlying problem was allocation students to hospitals after medical institution in the US. That was a huge computational problem, because the institutions had preferences of the students had preferences of the institutions, and the whole allocation was made in one day, so the whole country would go crazy. And actually this problem is translated into that. And the next application of that domain is kidney exchange, which is the saving life matter. So that's not that funny as I think. Although stable marriage is also important. Okay, see you next time.